Listo, profesor.
Dale. Buenos días a toda la comunidad latinoamericana. Esto es la red LAFMAT, Red Latinoamericana de Física y Materia Condensada y Ciencias Materiales. Red LAFMAT está conformada por varios investigadores de varias universidades de Brasil, Argentina, Chile, Perú, Bolivia, Colombia, Venezuela, Costa Rica, México. Eh, Good morning, everybody. This is the LAFMAT network. LAFMAT network is the Latin American network of matter condensed physics and material science. It is composed by members and professors from different universities in Latin America, from Peru, Brazil, Bolivia, Venezuela, Colombia, Chile, Argentina, Mexico, Costa Rica. Today, we have the invited speaker is Dr. Narasaiah Boya. Dr. Narasaiah Boya is from India. He studied chemistry under the supervision of our grand friend, Professor Badal Kumar, in Vellore Institute of Technology in Chennai. And he also made a postdoc position in University of Hyderabad in India as well, under the supervision of another professor who is our friend, Professor Pratap Kolu. Then Dr. Narasaiah moved to Peru. Now he's in Peru. He's doing a postdoc at the University of San Marcos in Peru, where he is working under the supervision of Professor Ángel Bustamante Domínguez in the University of San Marcos, Faculty of Physics. His specialty is chemistry. It is the green synthesis of different nanoparticles and their applications for the photocatalytic decontamination of purification of water. El día de hoy tenemos la presencia del doctor Narasaiah. El doctor Narasaiah es de India. Él estudió química en la Universidad de Vellore Institute of Technology en Chennai. Hizo su doctorado bajo la supervisión del profesor, el gran amigo nuestro, el profesor Badal Kumar Mandal, que es una eminencia en India. Luego hizo un postdoctorado en la Universidad de Hyderabad, en India, bajo la supervisión de nuestro gran amigo también el profesor Pratap Kolu. Luego viajó a Perú, en estos momentos se encuentra en Perú, en la Universidad Nacional Mayor de San Marcos, bajo un financiamiento, un proyecto del Concitec, Prociencia, haciendo un postdoctorado bajo la supervisión del profesor Ángel Bustamante Domínguez en la Facultad de Física de la Universidad de San Marcos en Perú. Su especialidad es green síntesis de nanopartículas para la purificación de agua y sus propiedades fotocatalíticas. Justamente es lo que va a hablar el día de hoy. Debido a que el doctor Narasaiah habla inglés, toda esta charla a partir de ahora es en inglés y la participación en inglés. Al público que nos sigue en las diferentes redes sociales, pueden dejar sus preguntas que al final de la charla les vamos a transmitir al doctor Narasaiah. Ok, doctor Narasaiah, welcome. You can share your screen and you can start your talk now.
Yeah.
We can see your screen now. You can start.
Yeah, good morning to everyone. I am Dr. Narasaiah Boya from India. So working as a postdoctoral researcher under Professor Angelo Bostomana. Today, and also here, I am in Peru, so University of San Marcos, working as a postdoctoral researcher. It is a great opportunity to me. I grateful thanks to the Concitec Pro Ciencias. So given this good opportunity for me. Thank you for so Concitec getting opportunity to me. Thank you. Today, hello, here is it audible my voice? Hello?
Yeah, go ahead.
Yeah. So today I'm going to give brief introduction about my work. So synthesis of nanomaterial and synthesis of superconducting YBCO HIPCO material by the green method and their application. So these are the presentation, my outline. The part one, it is considered as the preparation, introduction of the nanomaterial and preparation of the titanium dioxide material at various temperature. So part two, it is considered as a preparation of the superconducting material, HIPCO, so superconducting YBCO material by sol gel method and green method and solid state method, and their characterization. So part three, it is considered as a preparation of the palladium nanomaterial, green method, and its application, it is photocatalytic activity, reduction of the dyes and their characterization. And part four, it is considered as a preparation of the iron oxide nanomaterial. Okay, so different using as a substrate, so that is surfactant. So it is as a surfactant and their characterization. So introduction of the nanomaterial. The material should the size of the material dimension less than 100, it is called as a nanomaterial. Why the nanomaterial? Nanomaterial shows the different properties, that is mechanical property, thermal property, and catalytic property, and electrical and magnetic property. Due to this property, it shows the wide variety of the properties. It will show the different applications, a huge number of application of the material. So due to their application, so material is classified into different types of material, that is quantum dot material, iron oxide material, functional material, and composite material, and micromolecules, and polymer material, and so different mixed metal it is going to be used on based on their application. So now generally it is going to be considered the preparation of the metal, majorly it is two method, chemical method and green method. And by looking for the chemical method, producing agent is costly, and so it is required the high temperature. Reaction process, it is very slow, and define the size and shape of the material. While looking for the green and microplants, while looking for the green method, it is non-toxic, simple and rapid and low cost and high stability of the material, and reaction, it is going to be quick reaction, it is going to be completed. So that reason it is going to be particularly focusing of the research of the particularly focusing of the preparation of the material by green method. So while looking for the generally current trend, so once it is going to be dyes used for the various industries, leather industries, paper industries, and various food industry it is going to be. Once it is going to be wasted, directly it is going to be discharged into the river. Then ultimately it is going to be huge pollution, it is going to be occurs. Even 1 ppm of the dye, it is going to be very severe problem to the environment. So it is going to be degradation, it is going to be very difficult to the remove of the dye from the water. So industry water, it is going to ultimately it is going to be huge pollution, it is going to be ecosystem, the living organism. So that reason it is going to be more necessary to remediation method. So successive cheaper possible method, it is going to be degradation of the molecule, dye molecule. So these are the common dyes it is going to be used the various industries, that is cationic dye, anionic dye. So methylene is the cationic dye, rhodamide is the anionic dye, and azo dye is widely used for the various industries. So then ultimately it is going to be these dyes it is going to be used into the discharge into the river. So we can see here some photographs. It is ultimately it is going to be used the dyes in the various industries. They are going to be discharged into the river. Then ultimately it is going to be huge environmental pollution to the ecosystem. So that reason it is going to be required for the remediation of the methods. So successive cheaper possible. The best it is going to be research or focus in the particular for the environmental pollution required for the designing of the material. So for that it is going to be we are prepare the material. So that titanium dioxide material. So titanium dioxide material we prepare. So further it is going to be titanium isopropyl oxide dissolved in the salt, so distilled water. Then ultimately it is going to be, we are going to be add the extract. The extract it is going to be used the graph. So here grass extract we are going to be, initially it is going to be prepare the extract. So extract we are going to be so prepared. For that it is going to grass we are collected and dried at the room temperature. Then ultimately it is going to be grinded. So after that it is going to be, so we prepare the extract. So by applying for the heating, then ultimately it is going to be extract is going to be filter. Then we are going to be at the preparation of the material. So further it is going to be drop by addition of the extract. Then ultimately it is going to stir the formation of the brown color. It is, you can see here it is the reaction that is going to be carried out the titanium dioxide and material. Then ultimately it is going to be, so further it is going to be calculated at various temperature 300, 500 and 800 degrees. We are calculating the material. So this is the, so formation of the material. Initially we are going to be identify the, so titanium dioxide. Here it is going to be, so 300, 500, 800. So all the cases it is going to be formation of the nanomaterial is going to be confirmed by the UV visible analysis. So based on that it is going to be absorbance values. So each specific metal having the specific absorbance value, then it is going to be confirmed the material, it is going to be formation of the material. So further it is going to be analyzed, it is going to be a band gap value. So band gap value is very crucial for the, reduction of the dye. Here it is going to be band gap value is calculated by Tod-Platt equation. At 200 it is going to be 3.08 electron volts. At higher temperature it is going to be, so 3.6. That means increases of the band gap energy. So the smaller size of the material, lesser the band gap energy. So if it is lesser the band gap energy, also highly effective for the photocatalytic activity. So that means it is going to be photon electron also passes to the surface of the material. Immediately it is going to be generation of the electron. It is the advantage of the lower the band gap energy, so higher the activity of the photocatalytic activity. So further it is going to be analyzed for the, so band gap energy of the material. Here it is going to be, further it is going to be confirmed for the, so XRD analysis. XRD analysis it is going to be crystalline niche of the material, it is going to be confirmed. We can see here it is without calcination, there is no phase formation of the material. Whereas looking for the, so 300, 500, 800, it shows the phase formation of the material. All the cases it is going to be confirmed by the XRD analysis. It is going to be, so confirmed for the, so structure analysis of the material. Here it is going to be Serre equation, which is going to be calculated by the Debye equation, so size of the material, the crystalline size of the material. While looking for the 300, it is going to be less than 5 nanometer. At 500, it is going to be, so titanium dioxide is less than 10 nanometer. While looking for the 800 degrees, it is going to be, so 25 nanometer is going to be confirmed the crystalline size by doing, so Debye equation. While you can see here, it is clearly, it is a graph itself. Here it is going to be beta value, it is going to be less. So lesser the beta value it is going to, that means of the size of the material is very less. We can say here it is very sharp peak, it is going to be noticed, it's the higher the size of the material. So because it is going to be beta value, it is going to be, so very, so beta value it is very less. So that means ultimately it is a graph itself, it is going to be, which graph it is, which material it is going to be, smaller size of the material is going to be confirmed by, for the XRD analysis. So that's what it is, the XRD, it is the backbone of the material. While looking for the, so organic molecule or organic synthesis or drug, it is, so backbone of the, so confirmation of the material, it is NMR. So while looking for the powder XRD, so while looking for the material, it is confirmed by the XRD, it is the major technique for the confirmation of the material. So that means material, it is going to be the backbone of the, so material. Here it is going to be, and also it is going to be identify the, so commercial value. While looking for the synthesized material, commercial value it is shows the, so here it is shows higher the size of the material, it is equal to P25 brand name. So titanium, this is the titanium dioxide with the commercial value, it is 64 nanometer, it is going to be confirmed. So synthesized material, it is the smaller size of the material where, so prepare the material. So this is the XRD analysis, so XRD analysis of the, we can see is the full width of magnesia, so smaller size. We can see smaller the beta value, it's the higher the size of the material. See here it is the higher the beta value, it is the lesser the size of the material. So for it is confirmed by the XRD analysis of the, so three materials 300, 500, 800 degrees going to be identify the crystalline size of the material. Here it was going to be identify the, So TEM analysis. TEM analysis gets with the morphology of the material. So that means size and shape of the material it is going to be identified. We can see six clearly it is the particles are spherical in nature. Average particle rate is going to be around 5 nanometer. So here it is a different magnitude of the TEM image of the particle images of the at 300 degrees temperature of the material. So while looking for the displacing, it is so exactly matches with the oxide result. Here it is going to be a set pattern. It is give the clear information. The circular ring it is going to be so amorphous nature of the material. So it is going to be EDAX analysis will give the elemental analysis of the material. Well, so this is the lower temperature and this is the higher temperature. So lower temperature it is shows the very smaller size of the material is going to be prepared. While looking for the higher temperature, the 800 degrees Celsius, titanium dioxide material shows the higher the size of the material. Okay, so is the mean size is 29 nanometer. So different magnification of the TEM image of the particle, so TEM image of the titanium dioxide material. So here the displacing of it is going to be calculated. It is matches with the XRD result. And here you see a set pattern is going to be clear, indicate the circular ring on brightest spot. We can see at the lower temperature only circular is there is no bright spot. Here it is shows the circular in the bright spot it is going to be more crystalline nature of the material at higher temperature of the material. So here the EDAX analysis it is going to be confirmed by the elemental analysis of the material. So further it is going to be identify the titanium dioxide nanometer colloidal stability and thermal analysis. So stability analysis it is going to be identified while looking for the 300 and also lower temperature and higher temperature. We can see here it is lower temperature it is going to minus 45. Okay, so zeta potential. While looking for the higher temperature it is 33. So we can see here it is the lower temperature it is go more stability of the nanometer. Why? Because it is more stability of the material because it is very sharp peak. The sharp peak in it is going to go by higher stability of the material. So that means higher the zeta potential, whether it is positive or negative. So that is higher the stability of the material is going to be confirmed. We can see here it is going to be slope. So that means less are the stable of the material. Why here it is going to be very sharp peak indicators that means zeta potential it is going to be confirming of the material stability of the material. So smaller size of the material it is going to be the collision. So it is mobility of molecule. Mobility of molecule is the collision with the molecule. Then it is going to be repulsion. It is going to be occurs. Then ultimately it is going to be very sharp peak. It is going to be occurs in the lower temperature of the material. So that means smaller size of the material, higher the stability of the material. So here it is going to be. So thermal analysis. So thermal analysis it is going to be identify the stable of the material while looking for the lower temperature and higher the temperature. So lower temperature it is going to be more weight loss it is going to be more occurs. Where higher temperature it is going to be prepare the material. So weight loss it is going to be less. So that means is the lower temperature it is going to be molecule. So nanomaterial covered with the biomolecules. So covered with the we are going to be use the plant extract. The plant extract has a polyphenol. The polyphenols it is going to be reduce the metal ion. Then ultimately it is going to be surface it is going to be cover the biomolecule. The biomolecule it is going to be giving a higher temperature. Then ultimately it is going to be weight loss it is going to be occurs. That means moisture. So that means carbon content. Then ultimately it is going to be that is the weight loss of the material of the titanium dioxide nanomaterial. Yeah, so this is the application of the photocatalytic activity. So here it is identify the lower temperature of the material, so medium of the material, and the higher temperature of the material. So lower temperature, the titanium dioxide material shows the remarkable photocatalytic activity. Why? Because the smaller size of the material, then ultimately it is going the higher the photocatalytic activity of the dye degradation. While looking for the smaller size of the material, it is going to be degraded within short period 15 minutes. It is going to be degradation of methylene blue dye degradation. While looking for the higher temperature, it is going to be more sets of time. It is going to be degradation of the time. Why? Because lower temperature it is going to be smaller size. So smaller size of the material, higher the surface. Higher the surface, it is going to more number of the dye molecule it is absorbing of the surface of the material. Then ultimately it is going to be catalytic activity it is going to be increases. It is going to be so lesser the time it is going to be degradation of the dye molecule. Whereas without catalyst, we checked. Whereas in the presence of catalyst and without catalyst, we are looking for a without catalyst, there is no percent of the dye degradation. Whereas in the presence of catalyst, it is going to be gradually decreases the absorbance value. Then ultimately it is going to be higher the percentage of the dye degradation. It is going to be noticed. Yeah, so here it is photocatalytic activate the titanium dioxide metal, and so another dye it is going to be anionic dye. So it is rhodamine weight is we are taking. Similar weight is going to be so lower the material and higher the temperature of the material is going to be carried out. So similar it is going to be so degradation it is occurs with a short period. Then ultimately it is going to be it will be degradation, it is percentage, it is increases. So similar it is going to be catalyst and without catalyst. So with the presence of catalyst, UV light it is going to be passed. Then ultimately it is going to be photocatalytic degradation, superior photocatalyst of the material. Here it is going to be identified so different concentration and different amount of the catalyst and amount of the dye concentration. While looking for the amount of the catalyst, so where is amount of the catalyst it is going to be increases, the rate constant it is going to be increase. So that means it is going to be here it is going to pseudo first order it is going to be flat. So here it is going to be clearly so the amount of the catalyst it is going to be race constant it is going to be increases. So that means it is going to degradation time it is going to be decreases. And similarly with the amount of the effect of the concentration it is going to be we checked. So whereas amount of the dye concentration increases, what happened? So dye concentration it is going to be increases. So that means UV light it is going to be passes to the material. So that means more concentration. That means intensity is more of the dye molecule. So dye molecule it is going to be the lighting it is going to be passing to the dye molecule. So it is going to be penetrating to the very difficult because more intensity of the dye molecule. That means so inner filter effect. Due to the inner filter effect, so reaching of the catalyst it is going to be energy it is going to be reaching to the less amount of energy it is going to be reaches. That then ultimately it is going to be degradation efficiency is going to be decrease and required for the required for the time it is going to be required for the degradation of the dye molecule. So then ultimately efficiency it is going to be decreases. We can see here it is going to be at higher the 15 ppm it is going to be more amount of the time it is going to be take the degradation of the dye molecule. Here it is going to be photocatalytic with the possible mechanisms of the dye degradation. Here it is going to be material, the passing of the UV light. Then ultimately it is going to be electron transfer from the ground state to exit state, the valence band to conduction band. The conduction band electron it is going to contact with the oxygen molecule. Then ultimately it is going to be releasing of the superoxide material. So lower valence band electron hold it to contact with the water molecule. It will producing of the hydroxide radical. Here it is going to be active superoxide radicals. That means superoxide radical and hydroxide radical having the negative or radical. So that means negative, higher the electronegativity atom having the negative charge or higher the electronegativity having the radical, that is highly reactive. Why? Because it is highly reactive. So electronegativity having the already it is lone pair. So it is excess of the electron. Then it is going to be repulsion reaction. It is going to be occurs. Then ultimately it is going to be highly reactive of the superoxide radical and hydroxyl radical. So that means readily reactive with the dye molecule. Then ultimately it is going to be degradation of the dye molecule. If it is higher the electronegativity atom of the positive is that is more stable. Why? Because if the deficiency of the electron, then ultimately deficiency of the electron it is that is more stable, less reactive. So here it is higher electron having the positive negative charge, a radical it is going to be repulsion reaction occurs. Then ultimately it is going to be more and more it is going to be activated. It is going to be increases of the readily reactive with the dye molecule. Then ultimately it is going to be degradation of the dye molecule. So this is the outcome of the and summary of the conclusion. So first time it is going to be repaired the titanium dioxide using the gas extract, and crystalline size it is going to be very less of the material is going to be confirmed. So excellent temp result, and finally it is going to be outcome of the ACS published in titanium dioxide and material. Yeah. So further it is going to be here. Superconducting. So preparation of the superconducting. so YBCO material by sol-gel method. So sol-gel method, it is going to be more advanced to the solid state and conventional method. Why? Because it is going to be more homogeneity, it is going to be occurs in the solid state. So sol-gel method, the solution, it is going to be dispersed in the solvent, or ethanol, it is going to be used the distilled water. So further it is going to be, so YBCO material is going to be successfully prepared. So by sol-gel method, further it is going to be a stoichiometry, it is going to be calculated. So yttrium and barium and copper. So YBCO, so yttrium, barium, copper, it is going to be calculated based on the stoichiometry, then dispersed in the water. Here it is going to be, so copper stated is going to be take and disperse in the water, and barium stated we are going to be dispersed in the water. The final it is going to be, so yttrium, it is going to be dispersed in the water. Then after that is going to be used as a citric acid. For that it is going to be reduce the metal ion. Then ultimately it is going to be so adjusting the pH. This reaction mixture we can show that it is going to be very so precipitate type. It is going to be a reaction occurs due to the so citric acid react with the metal ion, then ultimately it is going to be form the complex. When it is going to form the complex, that means precipitation reaction it is going to be occurs. So further it is going to be, so this is the procedure of the material. So preparation of the YBCO composite material by superconducting composite material by sol-gel method. So metal salts, it is going to be weighed. Then after that it is going to be dissolved in the water. Then so stoichiometry. So based on the stoichiometry, say we are going to be calculated. Then after that it is going to be equal to the citric acid. It is going to be 1:2 ratio. We are going to the metal. So metal solution, metal salts, it is going to be precursor. It is going to be so addition to the so citric acid equal to the 1:2 ratio. Then ultimately it is going to be citric acid, it is going to be dispersed in the water. The final it is going to be added to the, it will form the precipitate, blue color precipitate. Then after that it is going to be add the, so adjusting the pH, the desired pressure is going to be around, it is 5 to 6. It is the preparation of the superconducting material. So then so after that it is going to be add the, so hot air balloon, it will form the so gel. So initially it is going to be dispersed in the water, and then ultimately it is going to be form the sol. Then adjusting the so reaction which is carried with the temperature, then ultimately it is going to be form the gel. So gel formation, it is going to be so hot air oven, it is going to be heated. Then ultimately it is going to be so calcinated at a so higher temperature. Then it will form the so it will form the so powder material. The powder material is going to be again reoxygenated for in the presence of oxygen. Then for the reoxidation, for that we are make the pellet. The pellet, it is going to be so calcinated again the presence of oxygen. Then it will form the YBCO superconducting material. So for here it is going to be confirmed by the YBCO superconducting material. So for the oxide analysis, it is going to be information of the so phase formation of the crystalline nature of the material. We can see the higher intensity of the peak, it is going to be superconducting material. So that means orthorhombic crystal structure, it is going to be added. It is matches with the standard JSPS number. Average crystalline size was calculated by Debye equation. Around it is 26 nanometer. So synthetic material, it is going to be confirmed with the YBCO superconducting material by oxide analysis. So further it is going to be analyzed further. So SEM analysis. So SEM analysis will give the clear information of the morphology. So size and shape of the material it is going to be identified. Here it is going to be SEM image, it got different magnification of the so randomly so compacted of the so size of the so compacted of the material, so randomly distributed. So here it is going to be elemental analysis, it is going to be confirmed by the EDAX analysis. There is no other impurity of the material. So here it is going to be so yttrium, copper, and barium element is present in the synthesized material. So element analysis, it is going to be identify the so EDAX analysis. Yeah, preparation of the superconducting material YBCO by sol-gel method. So here it is, there it is, we have prepared the so sol-gel method for the so preparation of the superconducting material. So solid state material, we have prepared the superconducting YBCO material. So for that it is going to be metal salts, it is going to be we are taking. So based on the stoichiometry, it is going to be calculated. So further, so it is going to make it as a so border, it is going to be make it as a mixed, and so around it is so 6 oxide, it is going molten crystal. Then ultimately it is going to be calcinated. Then further it is going to be make it as a pellet. Then recalcinated further in the presence of oxygen. So we'll get the so YBCO superconducting so composite material. So further it is going to be analyzed for the SEM analysis. So here it is surface of the material. See here it is going to be more. So in the presence of sol gel method, it is going to be so more compacted in the surface of the material. We can say here it is on the surface of the material. So material is going to be so small. So material is going to be so it will be the particles. It is going to be more dispersed, more in the so if we can identify the easily. So in the solid state material. So here it is redox analysis. It is going to be confirmed the material, the elemental analysis of the material. So there is no impurity of the material. So there is no other elementals present in the so redox analysis. So synthesis of the superconducting YBCO by green method. So for the green method, we are used for the plant extract. So here it is the fruit extract. So that is orange pills we are going to take. So that is make it as a pills. Then after that it is so dried at so room temperature 7 days. Then after that it is to make it as a so conventional grade. So make it as a powder. So then the orange pill it is make it as a powder and weighed at so 5 grams in the weight and disperse in the distilled water. The final it is going to be so heat it is going to be applied. Then so here it is going to be peel extract. It is contained has a so polyphenol. The polyphenols it is going to be while we are going to be applying the heat. So dissolve in the water. So in the dissolve in the water, we can say here it is going to be after that. Okay, so by applying for the heating, dissolving, then so filter the material. So filter the extract. So extract is going to be filtered using the water filter paper. Then ultimately extract it is used for the preparation of the YBCO superconducting material. So YBCO superconducting material, the plant extract it is going to be act as a play key role for the reduction of the metal ion. So that means yttrium, barium, and copper it is going to be reduced by the metal ion. So that reduced by the metal ion it is going to be so having the polyphenol. The polyphenols it is going to be reduce the metal ion. Then ultimately it is going to be stabilized. Then it is going to be applying for the heating. Then it will form the desired structure of the YBCO composite material. So this is the procedure of the preparation of the material. So here it is initially it is going to be take the metal precursor based on the stoichiometry it is going to be dissolved in the distilled water. Then finally it is going to be add the extract. So once it is going to be add the extract, it is going to be clearly shows the so green color of the so YBCO superconducting material in the presence of extract. While looking for the in the presence of chemical method, citric acid we are going to use. Here it is going to be form the so blue color of the material. By looking for the green method, it is so it is shows the green color of the very so noticeable of the color of the so YBCO superconducting material. So further it is going to be applying for the heating. It will form the okay so gel. Then after that you heat. So after that it is going to be heat the so oven. Then ultimately it is going to be form the so precipitate. The precipitate is going to be so hot air oven. Then ultimately it is going to be from the powder. The powder it is going to be same. We are follow the similar procedure. So calcium reoxidant will form the so desired products of the so YBCO superconducting material. So further it is going to be identify the analysis of the so material by the so SEM analysis. The particles it is the so SEM is the morphology of the material. It is going to be clear. The particles are visible in the okay so material. While looking for the sol gel method, while looking for the solid state method, while looking for the green method, clearly to shows the so material is so visible of the so more dispersion of the material in the so green method. So element analysis will give the information of the particles. So different elements, so elemental composition of the present in the so YBCO superconducting composite material. Yeah. So this is another material synthesis of the titanium dioxide material. So tin oxide material. Why? Because we have prepared the tin oxide material. So we are going to be incorporation in the tin oxide material in the YBCO superconducting material. So further it is going to be tin oxide material we are going to be prepared. So initially it is going to be metal salts we are going to be taking dispersed in the distilled water. Then we are going to be add the extract. So that means cotton pills extract we are going to be prepared. Then ultimately it is going to be add the extract. So drop by addition of the precipitate pump. Then ultimately it is going to be from the milky white color precipitate. The precipitate carefully we are going to be collected by centrifuge. Once we are going to be collected the centrifuge, we are kept for the outer oven. Then ultimately it is going to be make the precipitate at so calcinated 500 degrees. Then we will form the desired structure of the so tin oxide material. So this is the procedure of the preparation of the so tin oxide material. So here it is pills, it is extracted, is going to be prepared, then ultimately it is going to be hot and woven, then ultimately it is calcinated, we get the tinoxanol. Here it is mechanism, the possible mechanism of the tinoxanol, how it is going from on the tinoxanol material. So here it is going to be egg. So extract, the plant extract, it is going to be prepared. The plant extract, it is contained has a polyphenol. The polyphenol ultimately it is going to be reduce the metal ion. So tin plus 2 it is go, tin chloride we are going to use. So that means plus 2 oxidation start of the tin material. The tin metal it is going to be plus 2 oxidation, it is going to be reduced by the polyphenol. So that means polyphenols it is going to be reduced from the complex formation, it is going to be actress. The polyphenols it is going to be from the complex in the presence of tin material, then complex it is going to be formed, then ultimately it is going to be heating high temperature, it will form the desired structure of the tinoxide nanomaterial. So this is the possible mechanism of the preparation of the tinoxide nanomaterial. So further it is going to be confirmed the tinoxide nanomaterial by the UV visible analysis, and band gap analysis was calculated, and UV visible is going to be identify the formation of the material by the specific absorbance value. So based on the absorbance of specific metal having the specific absorbance value, so it is going to be confirmed with the material. So further it is going to be band gap analysis was calculated by top plot deviation. Then ultimately it is going to be zeta potential, it is going to be identify the stabilities of the collidation state, and solid state of the material is going to be thermally stable, also colloidal stable, it is identified. So further it is going to be identify the tinoxide nanomaterial. So XRD analysis. XRD analysis is a clearly it shows the clearly it shows the sharp peak it is going to be. So that means the crystalline nature of the material. So here it is going to be from the higher the beta, so that means beta value it is going to be very high. So very high, so that means smaller size of the material is going to be confirmed. The XRD pattern shows the multidisciplinary peak, which is Miller analysis. So which is Miller analysis confirmed by the standard standard mass software. There it is confirmed the JCPDS number. So average crystalline size by calculated by Debye calculation. So D equal to 5 nanometers. So further it is going to be identify the XRD analysis. XRD analysis it is going to be the information of the functional group of the material. So here we can see here it is going to the plant extract, they have the different various functional group in the plant extract. So that means hydroxyl groups and amine group. So and also it is going to be ketone group present in the plant extract. The plant extract it is going to be to reduce the material, and then ultimately it is going to form the material. So by looking for the only in the presence of material, so tinoxide material, so there is no surface of the material, there is no surface of the functional material on the tinoxide material. We can see here it is a very flat line. So that means there is no impurity of the material. Then metal only it is going to be present. So metal and oxygen. So that is tinoxide material is going to be confirmed the XRD analysis. So FTIR analysis. So Tema means, so here it is going to be further it is going to be confirmed the tinoxide material by Tema analysis. So Tema analysis will give the information of the morphology. So size and shape of the material is going to be confirmed. So morphology it is going to be the particles are spherical nature. The average particle size it is around it is going to be final. So it is going to be exactly match up with the XRD result. Here it is going to be day spacing, it is going to be calculated the interplanar distance. So interplanar distance of the plane it is going to be identified, which is good agreement with the XRD result. Here it is going to be set pattern is going to be clear information about the circular ring. It is going to be amorphous nature of the material. It is going to be confirmed. The element analysis is confirmed by the there is no other impurities of the present in the tinoxide material. Yeah, so prepare the tinoxide material, incorporated in the YBCO superconducting material. So further it is going to be make the material, so to incorporate it in the YBCO superconducting material. So superconducting material it is going to be, so we prepare the sol-gel method. So previously we prepared the sol-gel method. Similar way of protocol we are going to be followed. Why? Because it is going to be confirmed by the XRD analysis. So once it is going to be confirmed the XRD analysis, so we are going to be incorporating the prepared the tinoxide material. So tinoxide material the 2% of the tinoxide material incorporated in the YBCO superconducting material, and also it is going to be lower amount and higher amount of the tinoxide material is going to be incorporated in the material. Why? Because it is going to be incorporation of the material. so conductivity to superconductivity it is going to be increases. So for that, this nanomaterial is going to be enhancing of the superconductivity of the material. So for that, it is going to be so lower and the higher amount it is going to be. So 2 weight% and 6 weight% the tenoxide material is incorporate in the YBCO superconducting material. Then ultimately it is going to be enhancing of the. So I hope it is going to be enhancing the superconducting material. So that means spinning center in the. So pinning center it is going to be. So it will be create. So desired structure of the so YBCO superconducting material. Then ultimately it is going to be increases of the superconducting material. So here it is going to be preparation of the so superconducting YBCO material by hydraulic pressure, and we are so preparing for the so superconducting for the SEM analysis. So here he is Dina Vanako, my students. So preparing for the sample for the SEM analysis, and we are prepared for the so calcination analysis for the prepare the superconducting material. Here it is going to be while looking for the so 2 weight% of the material incorporated. So in the YBCO superconducting material, the morphology of the material have it is see. See here it is going to 2 weight per%, and here it is 6 weight per%. Clearly it is going to be so randomly distribution of the material here in the 2 weight% of the material. While looking for the 6 weight% the particles, you can see here clearly it is going to be spherical nature of the material The higher amount of the titanium dioxide incorporation in the so YBCO superconducting material. So we can see the morphology of the morphology of the material we can going to be easily notice. So here it is going to be the element analysis. It is going to be identify the redox analysis. We can see here it is lower amount of the so tin oxide metal incorporation in the weight% of the tin oxide is 1.75. While looking for the so high weight% of the we can say 7.39. So that means higher the percent is going to be confirmed the material is going to be so incorporation in the tin oxide metal in the YBCO superconducting material. Here it is successfully we have prepared the so YBCO superconducting material by sol gel method, and solid state method and grain method. So superconductive material is a grain method superior shows the SEM analysis. Clearly we are going to be notice the so particles in the so more dispersion in the material in the grain method, and also it is going to be prepare the sol gel method YBCO superconducting material by 2 weight% and 6 weight% of the lower amount of the nanoparticle and higher amount of the nanoparticle. It is going to be incorporation of the material. We can say here it is clearly SEM analysis. It is those the particles are more okay, so homogeneous in the so 6 of the particle we are going to be notice. So finally it is going to be successfully prepared the so 5 differences of the YBCO superconducting material. Yeah, so this is another preparation of the so palladium nanoparticle. So palladium nanoparticle, it is going to be huge application of the okay, so various application for the palladium nanoparticle. So that means organic transformation, or it is going to be biological activities, which is well known for the so palladium catalyst. The palladium catalyst it is going to be so we prepare the palladium nanoparticle. For that it is going to be prepared the extract. So once it is going to be prepared, the extract is going to be add the palladium palladium solution, the metal precursor. The metal precursor it is going to be reduced by the polyphenol. Then ultimately it is going to be oxidized by the polyphenol. Then it is going to be stabilization of the material by polyphenol. So by polyphenol of the surfactant of the material. So here it is going to be confirmed by the so palladium so nanoparticle by UV visible analysis and dynamic light scattering. The stability analysis is going to be identified. So initially it is going to be identified the UV visible analysis. The extract it is going to be identified the UV visible. Whether it is going to be extract having any so functional group or not. We can see here it is going to be to so absorption band it is going to be noticed. That means it is extract having of the functional group. So that means it is going to be here it is going to be so N2 pi and pi2 pi it is going to be extract. So that means polyphenols it is going to be transition, it is going to be actors. Then it is going to be confirmed by the biomolecule, it is going to be present in the extract. So extract it is going to be addition to the nanoparticle. There is no okay, so absorption value. Why? Because it is going to be polyphenols, it is going to be reduces the metal ion. Once it is going to be reduce the metal ion, it is going to be clear the single absorption factor. It is going to be notices of the palladium nanoparticle. So further it is going to be identify the stability and the colloidal state. So while you're looking for the colloidal state, it is going to be identify the higher the stability of the material. We can see it's minus 57. So here it is higher than positive charge or higher than negative of the zero potential, more stable of the material. Why? Because higher the positive charge, that means colloidal of the charge. So particles it is going to be so interact with the magnet field will give the higher the negative value or positive value. So that means it is going to be so more stable of the material. It is going to be come from the palladium nanomaterial. Here it going to size also it is going to be identify the zeta potential. It is going to be average size of the material is going to be 20 nanometers. Further, it is going to be identify the XRD and FTA also. The XRD pattern is goes the clear, it is goes a multidisciplinary plate which is corresponding to the measurements. So, and a synthesized material is going to be confirmed to the JCPDS card number. Average crystalline size was calculated the best calculation D equal to 10 nanometer. So here it is going to be identify the polyphenols. Here we are checking for the only for the extract. The extract it is going to be shows the different functional group in the extract. That functional group it is going to be so reduced to the metal, then ultimately it is going to form the material. So still it is going to be without it is so still it is going to be so polyphenol the surface of the material. Here it is going to be only extract is going to be identified FTNs. Here it is going to be only it is going to be identify the palladium nanomaterial. We can say here it is going to be so polyphenols. So that means it is going to be biomolecules. Biomolecule it is going to be reduced and capped to the nanoparticle. So having a capped nanomaterial, so capped material is going to be superior for the catalytic activity. While it is a functional material, the material is going to be so covered with the biomolecule. That means ultimately it is going to be so enhancing for the catalytic, so enhancing for the catalytic activity or potential for the catalytic activity. So further it is going to be we are analyzing for the FTA analysis confirm the biomolecule on the surface of the material. So various functional group it is going to be based on that it is going to be wave numbers it is going to be notice different standard wave numbers. So which is standard wave numbers based on that it is going to be identify the various functional group. Yeah, so application we are done here for catalytic activity for the reduction of the azodize. So azoda is widely used for the different various industries. Then ultimately it is going waste it is going to be directly discharged into the river. Then ultimately huge pollution it is going to be occur. For that it is going to be we are particularly focusing for the azodize for the reduction of the azodize. For that it is going to be Congo red we are going to be take while looking for the whereas the presence of only without catalyst there is no degradation of the reduction of the dye. So sodium borate it is going to be added, it is going to be hydride ion it is going to be released. Then ultimately here it is going to be a reduction reaction occurs in the presence of catalyst. While looking for the catalyst, it is gradually decreases of the absorbance value. So that means in the presence of catalyst it is going to be here it is clearly noticing of the absorbance value gradually decreases the absorbance. That means reduction reaction it is going to be occurs. So further it is going to be identify the kinetic plant reduce fast the pseudo first order reaction. While looking for the where the amount of catalyst it is going to be the rate constant was increased. So that means it is going to be faster reaction it is going to be occurs. Where amount of catalyst it is increases, there is more amount of the constant of the dye concentration. So more amount of the catalyst it is going to be increased. So the surface activity it is going to be more number of the active sites. Then ultimately it is going dye molecule is going to be degradation it is going to be faster. Whereas in the presence of amount of the catalyst, amount of the dye concentration it is increases, the concentration of the dye increases, then ultimately is going to be more competitive of the dye molecule. So that means it is going to be fixed catalyst of the catalyst, the sufficient of the active sites it is going to be less. Then ultimately it's more number of the dye molecules. It is going to be degradation. It is going to be decreases of the dye degradation. Why? Because it is going to be the active sites it is going to be limited numbers of the active site type. Then ultimately it is going to be degradation time rate is going to be decreased. We can see here it is going to be whereas amount of dye constant is the red constant was decreased. Yeah, so this is the catalytic of the reduction of the dyes. So that means it's a different azo dyes we are taking. So sunset yellow and methyl argent. tartargene. So these are the food dyes we are going to be used. So here it is going to be all the dyes, it is going to be decreases of the absorbance value based on the presence of extract. While looking for the in the presence of extract, it is going to be a gradual decrease in the absorbance. We can see clearly to notice the dyes it is going to be after it is a certain period, it is going to be decolorization of the, so that means reduction reaction it is going to be occurs in the presence of extract, in the presence of sodium borate. The optimized here, it is going to be optimized catalyst. So the optimized sodium borate is sodium borate we are going to take, and sufficient to the amount of the so catalyst it is going to be the gradually it is going to be decrease the observation. So higher the percent of the dye degradation it is going to be noticed. That means around it is going to be 98%, 90 and 90 above 95%, 95% it is going to be decreased in the presence of catalyst. Yeah, so this is the possible mechanism of the dye degradation. While looking for the presence of catalyst, so in the presence of sodium borohydride, the electron it is going to be released. Then electron it is going to be capture the hydride ion. Then it is going to be lead the azuride reaction. So azuride, so hydride ion it is going to be so reducing of the azo bond. Then ultimately it is going to be from the smaller entities. So dyes it is going to be oxidized form to reduced form. It is going to be reduction reaction. It is going to be azo bond. It is going to be a break. Then ultimately it is going to be a smaller entity. It is going to be formed. So it is going to be a smaller entity. Less toxic and there is no toxic to the environment. Similar way, it is going to be proposed the azuride degradation in the presence of catalyst. So methyl ion is a congruent. So azuride we are going to be mechanism is to propose. That means hydride ion it is going to be the presence of catalyst. It is going to be absorbing of the hydride ion. Then ultimately it will diminution of the activation energy in the presence of barrier. So that means it's a dye molecules and sodium borate. So catalyst it is going to be acting as a mediator. It will be upcycling of the hydride ion. Then ultimately it is going to be transferred to the dye molecule. It is going to be do the reduction reaction. It is going to be occurs to the from the smaller entities of the dye molecules. Yeah, so this is the HPLC analysis. Really, it is going to be so polyphenols it is present in the biomolecules, it is going to be present in the extract. For that, it is going to be extract, it is going to be analyzed for the high performance liquid chromatography. It is also different, it is going to be retention value. So this retention value it is going to be matches with the standard value. So that means it is going to be exactly retention time it is going to be matches with the since plant extract manner. So that means it is going to be these are the these are the polyphenols it is going to be present in the extract. So based on these polyphenols extract, how it is going to be reduced and how it is going to be capped in the biomolecule, it is going to be propose a mechanism. We can see here it is going to be clearly the molecule it is going to be polyphenols it is going to be reduce the metal ion, then reduce the metal ion, it is going to be capped to the capped to the nanomaterial. So that means it is going to be stabilization of the material. The stabilization of the material is going to be based on the inter and intermolecular hydrogen band. So inter and intermolecular hydrogen banding it is going to be occurs in the complete stabilization of the material is going to be confirmed. So that means it is going to be higher the stability of the material. Why? Because it has zeta potentiality shows the very high -57 point. That means very more stable of the material. Why? Because it is going to be the molecule nanomaterial it is going to be stabilized with the material. Why? Because polyphenol it is going to be capped and reduced and capped to the capped to the nanomaterial. So then it is going to be shows the higher the stability of the material, and also it is going to be identify the biomolecule it is going to be further it is going to be confirmed with the FTA analysis. So we can see clearly it is going to be functional group it is the present in the extract. Even it is plant extract it is, and nanomaterial it is shows the clearly functional group it in the FTA analysis. So here it is going to be outcome. It is going to be published the this part of work. It is going to be science director. Yeah. So based on this idea, we prepare the similar. It is going to be iron oxide nanomaterial. So they based on the stabilization mechanism, whether it is going to be work for the chemical also. So whether it is going to be plant extracts, plant extract, similar way it is going to be here. It is going to be use the plant extract for the stabilization of the material. we can see here it is going to be FT analysis is going to be identify the functional group on the surface of the material. So functional group it is going to be capped on the nanomaterial. So for that, here we propose the similar work. It is going to be preparation of the iron oxide nanomaterial. So further it is going to be used in the presence of plant extract, in the presence of arginine, so in the presence of lysine. So how it is going to be prepared the nanomaterial. So here it is going to be prepare the material. So iron solution for the +2 oxidation +3 oxide is going metal sulfate is going to be dispersed in the water. Then after that it is going to be as the reducing agent. So that means reduce the metal ion, they reduce the metal ion, and it is going to be stabilize the metal by adjusting of the pH of the by using NaOH around it is 11 pH. So pH it is 11. Then it is going to be reduce the metal ion, it is going to be capped the molecule. So here it is going to be L-arginine and lysis it is going to be reduce the metal. The further it is going to be further it is going to be the capping of the further it is going to be capping of the material. Here we are confirm the material it is going to be UV visible analysis is going to be the formation of the material is going to be INF. The base analysis is going to be absorption value. The specific metal having the specific absorption value, it is confirmed with the UV visible analysis. It is going to be transition of the electrons. It is going to be occurs in the presence of extract, and a similar way it is going to be L-arginate is going to be capped with iron oxide. Biomolecule it is going to be capped the iron oxide. So L-arginate is going to be capped the biomolecule. It is going to be all the cases it is going to confirm with the UV visible analysis. So lambda maximum. Here it is going to be identify the band gap energy value. While looking for the biomolecule, it is going to be 1.3 electron value. While looking for arginine and captain, it is going to be higher. So band gap energy it is going to be noticed. So that means biomolecule it is going to be more competing for the. So it will be reduced the metal ion. It will form the smaller size. So smaller size than it is going to be pinching of the material. Then ultimately it is going to be the band gap it is going to be very less compared to the L-arginine and lysine. Here it is 1.6 to 1.8 in the presence of L-arginine. Yeah, so here it is identify the functional group, identify the FTA analysis. While looking for the only it is going to be extract is going to be multifunctional group, it is going to be present. While looking for the biomolecules, that means it is going to be plant extract it is going to be used. Here it is going to be nanomaterial, it is going to be multifunctional group, it is going to be present in the surface of the material. So that means it is going to be material it is going from and covered with the capped with the biomolecule on the surface of the material. So similar case it is going to be, we can see L-arginine is also it is going to be iron oxide material. It is capped with the biomolecule on the surface of the material. The capping of the L-arginine on the surface of the material. So similar case it is going to be L-lysine. So iron oxide nanomaterial is going to be confirmed by UV visible analysis, and X-ray it is going to be FT analysis it is going to be the capping of the surface of the material. So that means it is going to be reduce the metal ion, then it is going to be capped on the surface of the material. So that means it is material having the cap and functionalized material, superior catalytic activity, high potential catalytic activity of the material. The material having the capped material, the functionalized material, so it is shows the huge potential shows the material. So further it is going to be, we prepare the different iron oxide material, functional material it is going to be prepared. Yeah, further it will be confirmed by the hexadenal. It is shows the clearly it is shows the indications of the all the cases it is going to be biomolecules and L-arginine and L-lysine it is going to be this L-lysine it is going as a surfactant. So it is going to be reducing agent. Surfactant reducing agent is going to be reduce the metal ion. Then ultimately it is going to be shows the crystal crystalline nature of the material is going to be confirmed. While looking for the biomolecules, so that means going to plant activity shows the multidisciplinary plate is going to be confirmed with the hexadenals. In the case of L-arginate is going to be confirmed with the crystalline nature of the material, and also similarly L-arginate is going to be confirmed the crystalline nature. While looking for the biomolecule it is going to be a crystalline size of 15 nanometer. While I was looking for the L-arginate, the very sharply compared to the biomolecule. Here it is going to be 21 nanometer is going to be the Debye equation. Similarly, it is going to be L-arginate is going to be confirmed by the crystalline size of 18 nanometer. We can see here it is going to be liquid state and solid state. How it is going to be magnetic property. See, we can see in the solid state material. So how it is affected into the magnetic. So there is, so in the, even it is the up and active, so here is strong magnetic of the material of the synthesized material. While looking for the even liquid state also, you can see here it is going to magnet property of the synthesized material. Yeah, we can see video, I'll play. Yeah, we can see here it is. So in the liquid state, we can see it is going to be the powder, it is going to be, we are keeping one side in magnetic. Yeah, here it is magnetic in the liquid state, here it will be attracting of the so material. So liquid state, even it is the liquid state, we are keeping the magnetic, it will be so upcycling of the material in the so one side. Yeah. So this is the stabilization mechanism of the stabilization of the iron oxide nanomaterial. So iron oxide nanomaterial, say having the in the presence of extract, the presence of so plant extract, the plant extract having the different so polyphenols compound. The polyphenols, it is going to be reduce the material and stabilization of the material. So iron oxide material is going to be stabilize the polyphenol. So where is polyphenol, it is going to be added to the plant extract. So that polyphenol, it is going to be reduce the material. Then ultimately it is going to be stabilize the so intermolecular hydrogen bonding. So through the hydrogen bonding, entirely it is going to be so stabilization of the material. So stabilization of the material, it is going to be so confirmed by the. Okay, so based on the FTR, so based on the FTR, it is going to be identify the, so based on the, so HPL also it is going to be identify the various functional group. The functional group, it is going to be functional components, it is going to be identified. So based on the component, it is going to be stabilization mechanism proposed. So HSB principle, it is going to be applied. So whereas it is going to be, the metal, it is going to be soft metal and hard metal, then ligand, it is going to be act as a, so hard ligand, then ultimately it is going to be more stable of the, so material is going to be confirmed by the stabilization of the material. So similar way, it is going to be proposed the L-arginine. The L-arginine, it is going to be capped to the so iron oxide nanomaterial. How it is going to be so stabilized, it is going to be material. So okay, so base similar way, it is going to be proposed the so inter and intermolecular hydrogen bonding. So then ultimately it is going to be the stabilization of the metal, iron oxide nanomaterial. L-arginine is going to be capped to the so L-arginate is capped to the surface of the material, iron oxide nanomaterial. Here it is going to be proposed the so iron oxide nanomaterial by using L-igen. L-igen, it is going to be reduced. Then ultimately it is going to be capped on the surface of the material. We can see it is going to be a very beautiful structure of the material. We proposed on the inter and intermolecular hydrogen bonding, stabilization of the material. So in the three cases, it is going to be proposed the so mechanism stabilization mechanism of the L-arginine and biomolecules. So it is going to be shows the very clear. It is going to be smaller size of the material. It is going to be noticed. Just that means quenching of the material is going to be occurs. Then here it is going to be iron oxide material. It is going to be so based on the inter and intermolecular hydrogen bonding. It is going to be stabilization of the material. Then ultimately it is going to be so this iron oxide material is capped with the biomolecule. Then ultimately it is going to be superior for the so catalytic activity for the so various we are going to be applying for the so reduction of the water treatment, so pollution, so environmental pollutant degradation, or so water treatment, we are going to be applying the so reduction metal. And also it is going to be effective work for the heavy metal removals. So in the soil or so water, it is going to be contained as a heavy metal. Then ultimately this biomolecule is going to be capturing the heavy metal. This also it will work for the removal of the heavy metals. Yeah. So finally, it is acknowledgement great. So it is going to be a grateful thanks to the so constitutive proficiency giving this good opportunity to me. So wonderful opportunity to me. I really sincerely thanks to the so funding agency Constitutive and process here good opportunity to me. So I am working as a postdoctoral researcher under the supervisor of Professor Angelo Bostomano. So it is Angelo Bostomano giving a good opportunity to me. Thank you very much, sir. And also I sincerely thanks to the so Professor Luis Santos. His Luis Santos is going to be some valuable social inputs for the so giving so great so this so continuously it is going to be a support and providing to the valuable suggestion to the so further it is going to be occurs to the end so this work. Really thanks to the Professor Luis Santos giving the opportunity to me and valuable suggestion and continuous support till to the today. Yeah, this is the ceramic nanometer in the laboratory. So University of San Marcos provided to me great platform to me providing to me. So thank you very much to the university and thank you. So finally, thank you for the please attending kind attention. So this is the Taj Mahal, India. So this is the Hyderabad. So Hyderabad, India. Thank you very much. Thanks for all.
Okay, very nice. Thank you very much, Dr. Narasaiah, for your nice talk.
Yeah.
And now we are going to move to the questions, just to say if para el público que nos está siguiendo a través de las redes, si tiene preguntas, puede ir dejando a través de las redes sociales donde está siguiendo esta transmisión. Al final pues, vamos a leer sus preguntas. Muy bien. Now we are going to start with a question from the panelists today.
Yeah.
We are going to start just with your supervisor in the University of San Marcos, in Faculty of Physics, Professor Ángel Bustamante Domínguez. Ángel, do you have questions?
Sí, Luis. Rápidamente en español te digo, pregúntale qué segundas fases encontró en la preparación del IVACO con sol gel. Si ha habido segunda fase así pequeñas, así.
Okay, Professor Ángel Bustamante, Professor Ángel Bustamante is asking about in the case of the YBCOs by sol gel.
Yeah.
Which secondary phases have you found?
Yes. Yeah, so secondary phases it is found actually. So based on the calcinate it is more so accurate by looking for the where calcinated the material. Okay, so the YBCO superconducting material, so 80 degrees temperature. So more it is going to be superior, so superconducting material. So around it is 910 to 940 degrees temperature. We are going to be applying for the around temperature. It is going to be if you will give. Okay, so 910 to so 940 degrees temperature we are going to be, so calcination we are going to the material, so that means that there will be no secondary phases will be formed. Why? Because we are calcinated the material at 880 temperature. 880 temperature it is going to be, so in the XRD pattern it is shows the very minute very so less amount of the so secondary phases it is present, so copper oxide it is going to be formed. Absolutely so right it is. So because of the so due to the temperature it is going to be formed, the sol gel method is going to be completely the homogeneous of the material. So that means it is going to be sol gel, it is going to be more advanced to the so solid state metal. Why? Because it is going to be the metal salts, it is going to be dispersed in the so solvent, so that then ultimately it is going to be solvent is going to be so dispersed in the salts, it is going to be more so homogeneity it is going to be occurs. That homogeneity it is going to be occurs, it is going to be from the so material, so more chances to the so other phases it is going to be formed. While going to be applying to the so temperature, that means going to be crystalline nature it is going to be increases, while it is going to be certain period of the material it is going to be with specific so temperature it is going to be from the desired structure, stable structure it is going to be formed. So that means it is going to be around it is 910 to so 940 degrees temperature will form the so stable structure of the superconducting material. So that means we are going to be so another cycle we have to going to be do apply, so around it is okay, so temperature will so avoiding for the secondary phases of the material.
Okay, thank you very much. More questions, Ángel?
No, gracias.
Okay, yeah, thank you very much. Esperemos que el profesor Ángel se mejore pronto y esté con nosotros nuevamente. Y ya salga bien de su operación. Bien, vamos, let's go with the questions from there are some students. Hay algunos estudiantes de Kazajistán el día de hoy. Some students from Kazakhstan.
Okay.
If they have questions from the Kazakh students.
Can I ask?
Okay,
Yeah, please.
Juga. Go ahead, Suga.
Thank you very much for your.
Suga,
Thank you
sorry, could you
for.
open your camera? Open your camera, please, Suga.
Okay. One moment. Can you
Yeah,
see
go
me?
ahead. Yeah, go ahead.
Thank you for your presentation and for sharing with your work. And I interest about the green synthesization approach. What were the main challenges in synthesizing using a green approach?
Yeah. So your main challenges, it is a green sense of the material. The material it is going to be, the product it is going to be very less amount of you are getting. Why? Because the extract it is going to be the product final. So we are preparing the desired products and the smaller size of the material we are going to be prepare. The challenge it is going to be, so applying for the, so extract is going to be prepared and we are going to be apply the desired product, the weight of the product. So that means amount of the product we are going to be less. So in the presence of green extract, while looking for the solid state method or sol-gel method, we are so huge amount of the product we are going to be so we will get. While looking for the green method, the product it is going, the final desired product we are going to be less, and also it is going to be the polyphenols. We can see the some season it is going to be is the plant. So plant it is going to be, well, it is going to be, that means it is going to be, so some season we looking for the, so winter season, while looking for the, so summer season. So while looking for the summer season, when the plant it is going to be, so that means the polyphenols it is going to be in the season also it is going to be so vary. While we prepare the nanomaterial, so in the summer season we prepare the nanomaterial, same material, the plant material we are going to be use, and so very different season it is going to be, so we can so apply that also it is going to be so varying of the material, and also it is going to be so more eco-friendly. So we are not using any huge hazardous solvents, so we are going to be not very costly so material. So in the simple process we are going to be, so room temperature we are going to be carried out the material, the reaction it is going to be carried out, and we are going to be also applying for the material. So we are applying for the metal solution, then ultimately desired structure it is going to be so we will get the material. So that is the more advantage of the material. The thing it is going to be, so the material is going to be, so product is will get the so less. So apart from that, it is eco-friendly to the nature, eco-friendly to the environment, and so we can carry it out to the and also it is going to be more cost effective. So that is the more advantage of the green process. So it is a less cost. So there is no, we are using any so solvents and hazardous. In the simple process we are going to be carried out. So that is the more advantage. The drawback it is going to be the season wise it is going to be applying of the material, and also it is going to be the product it is going to be, that is the more challenging in this of the material. So still it is going to be focusing of the material of the by the green process. Yeah.
Okay, Suga,
Thank
do you have
you.
more questions?
No,
Okay.
thank you.
Okay, thank you very much, Suga. Well, let's continue. And, el día de hoy tenemos estudiantes de Kazajistán, de la Universidad de Eurasia National University, Universidad Nacional de Eurasia, que están haciendo preguntas. Ellos hablan inglés. Perfecto. Another student, participant, Aslan. Open your camera, please.
So, yeah, wait a minute. Have you seen me?
Go ahead.
Thank you for your presentation, Dr. Boya. Sorry, I have a question about the what limitation does green synthesis have compared to conventional techniques, and the future of the green synthesis?
Yeah. So while looking for the green synthesis, while looking for the chemical synthesis, so chemical synthesis, okay, so desired structure it is going to be, so that is the, we can see here it is first. Yeah, so while looking for the chemical synthesis reaction process, it is going to be very slow, and so require the high temperature, And also it is going to be several steps it is going to be required. Reducing we are going to be able to, so solvent we are going to be apply, and organic solvent we are going to be apply. So salt it is going to be does not dissolving the solvents. That is the more drawback in the chemical method. Well, reducing agent is very costly. And so define the size and shape, but it is going to be require the high temperature, and also it is required the so specific solvent it is going to be require the specific precursor solutions. Based on that precursor solution, it is going to be dispersion it is going to be required. So then only reaction it is going to be occurs. So that is the more drawback in the chemical methods. While looking for the green method, it is non-toxic, so simple and rapid it is going to be reaction. It is going to be very quick reaction it is going to be occur, and low cost and high stability. The stability also you can see it is the palladium nanochemical shows the very high stability of the material. So even it is going -57, so that means very high stable of the material. So the zeta potential is going to be confirmed by the plant extract. It is shows the high stability of the material is going to be confirmed, and also it is going to be a reaction. It will be the rapidly reaction. It is going to be occurs. So quick reaction it is going to be occurs with desired process we are going to be. So we will make the green synthesis, and green synthesis also it is going to be more eco-friendly. So more eco-friendly to the environment, and so there is no toxic to the environment. And the simple process we are going to be carried on, and desired structure it is going to be carried on. So that is the more advantage of the green method. So it is going to be as per the standard. So 12 principle. So green chemistry. So green chemistry is going to be 12 principle. The 12 principle is going to be agreed to the by the green process. Or it is that means environmental hazardous, eco-friendly, or so safety to the, and so pollution to the, so based different so 12 principle of the green chemistry, that it will be 12 principle it is going to be obeyed to the, so it is going to be also obeyed to the green synthesis process is going to be considered, so that it is going to be more advantage to the as compared to the chemical and physical method. The physical method also it is going to be used, it is going to be applying the pressure, and it is going to be ball milling and laser printing. So high so laser printing it is going to be applied. So different technique it is going to be applied. So among all this, then by looking for the green method, that is more and more and desired product it is going to be applied. We can see it is going to be titanium dioxide below. So that means less than 5 nanometer it is going to be desired the material by plant texture. So that is the advantage of the material. So that means the plant texture it is going to be reduce the material and pinching of the material. So smaller size of the material, even it is going to be the plant texture it is going to be actually as a reduced, and it is going to be the smaller size of the material. Also we are preparing the desired structure, and so desired structure of the material. So that is the more advantage of the green processor.
Okay.
Thank you for your answer.
Yeah.
Okay. Thank you, Aslam, for the question. Dina.
Okay. Hello.
Can you activate your camera, please?
Okay, yeah. It's okay?
Yeah, go ahead.
So, thank you to your presentation. And my question is, which components in the plant extract play the main role in reducing and stabilizing the nanoparticles? So, and how can this be proven?
Yeah. So the plant extract basically it is having the polyphenols. So polyphenols, we can see here it is going to one plant extract. We are identify the HPLC. So HPLC chromatogram. So HPLC chromatogram it shows the multi peaks. That peaks it is going to be matched with the standards. So it is going to be matches with the standards. So based on the retention time, so it will be identify the polyphenols. That means so different various functional group, various polyphenols compounds it is going to be phytochemicals. Actually it is phytochemicals. The phytochemicals it is going to be play key role. So by the phytochemicals it is identify the high performance liquid chromatography. So liquid chromatography will give the information of the plant texture of the retention time. Based on the retention time it is going to be matched with the standards. We can see it is drugs. Okay, so HPLC it is going to be identified. So cocaine or some it is going to be drugs, it is going to be which peak it is going to be major, it is going to be in retention time. So that means the component is going to be identified. So it is going to be pumped to the HPLS. So based on the retention time, so that which is highest intensity peaks. So that means that product or so that material having the cocaine. So based on the written step, which peak it is going to be, where it is peak it is going to be coming. So that peak it is going to be responsible for this functional group. So this responsible for that compound. So that material having as that compound. So similar it is going to be plant extract, it is going to be so analyzed for the HPLC analysis. That HPLC also where it is going to be retention time here occurs. That retention time occurs based on the standards we are going to be carried out. So that carried out it is going to be polyphenols. So that carried out it is going to be ascorbic acid, gallic acid, pyrogallic, and ellagic acid present in the extract. These phytochemicals present in the extract, that phytochemicals it is going to be reduce the metal ion. We can see it is so tin oxide metal we represent the mechanism. The tin oxide it is going to be that polyphenols it is going to be reduce the metal ion. So that means the metal ion is going to be tin oxide it is going to be +2 oxidation state. So +2 oxidation state is going to be reduce the +2 ions. So that means polyphenols it is going to be reduced. So it is going to be 0 oxidation state the tin oxide metal. So tin oxide metal it is going to be 0. Then it is going to be polyphenols. It is going to be form the complex formation. The metal ion, so it is going to be combined with the polyphenols. The metal ion it is going to be combined with the polyphen. When it is going to be metal ion, it is going to be reduced and combined with the metal ion, it will form the precipitate. So the solution we are applying for the plant extract, the extract it is going to having the polyphenol, biophenol. So that means it's a biomolecule. So the biomolecule is going to be reduced to the metal ion. So then reduced to the metal ion, then ultimately it is going to be from the complex formation. When it is complex formation, it is from the precipitate. The precipitate it is going to be occurs. It is going to be further reaction. It is going to be occurs in the heating apply. Then ultimately it is going to be desired structure of the material. So that means it is going to be polyphenols. It is going to play key role. So it is reduce the metal ion and stabilization of the material, then capping of the material. Then ultimately 3 process it is going to be occurs for the preparation of the nanomaterial by using plant extract, by using any plant. So we can see it is, we can see here, so any plant also it will be, so generally it is going to be plants having of the polyphenols. So which plants, which material it is going to be occurs, we identify the by HPLC analysis, or it is going to be another by the GCMS analysis. We are going to be based on the mass, we are going to be identifying. So GCMS analysis and also preliminary analysis. While before it is going to be started, so we can easily noticing for the preliminary analysis. We take the extract, we are add the some chemicals, folinic coil. So that means folinic coil and carbohydrate test, phenol test, aniline test. And so there are the multiple phytochemical analysis tests is there. So we can run the extract, we are going to be take the different applying for the material. So based on that extract it is going to be give the color. Okay, so color, based on the color it will give. Okay, so if it is in the purple color, that is polyphenol. So for folinic test, so we are going to be apply the chemical to the folinic test. So extract it is going to be add, then ultimately it is going to be the color. So that means that compound it is going to be present in the that extract. So based on the identify the preliminary analysis of the phytochemical test, and also it is going to be polyphenols, quantification and qualification, both is there. So qualification test and quantification, and how much amount of polyphenol present in the extract. So by standard measurement it is available. Then based on that quantification also, how much quantity, so how much grams. Okay, so 1 gram of the plant extract, how much milligrams it is going to be present in the extract, we are going to identify. Based on that also it is going to be identify the in the polyphenols. So that polyphenols it is going to be reduce the metal ion. Then ultimately it is going to be stabilization of the metal also. We are proceed the material. So that is the general characterization of the before applying for the material, before applying for the material. So pre-analysis it is identify the various functional group, various it is going to be biomolecule it is going to be present in the phytochemicals present in the extract, identify. So once it is going to be identified, then it is confirming with the stabilization, confirming with the for the preparation of the material. And also it is going to be another technique, it is going to be used for the column method. So we are going to be use the solvent, then applying for the extract, then it is going to be column. So column you are going to be run, then extract it is going to be run in the solvent, That means extract it is going to be dispersed in the solvent. The solvent it is going to be run the HP. So we are going to be run the NMR. So column method. So that means a TLC. So TLC method also it is going to be identify the polyphenol. So that is the more. So the drawback it is going to be the quantity of the material. So that means it is going to be, you are getting the milligrams. So by column it is going to be, will get the compound. That compound it is going to be identify the say NMR. So by NMR also it is going to be identify the desired structure of the material. So having the various organic compounds present in the extract, that is also one technique is there. So based on different technique, we are going to identify the various polyphenols present in the extract. So that extract it is going to be, so it is suitable for the high reach of the quantity of the polyphenols. It is more suitable for the reduction of the metal. Then ultimately we are getting the desired structure of the material. Yeah.
Thank you. Then it was more understandable. Thank you.
Yeah, it is really good question.
Thank you, Dina. Now, Sarina.
Hello. My question is based on your work with orange peel extract. I want to ask what prospects do you see for using green synthesized nanoparticles in next generation superconductor devices and energy applications?
So energy application and superconducting material by using plant extract, the orange peel extract. So really it is orange peel, it is have the multiple polyphenols. That polyphenols it is going to be, so that means the YBCO superconducting material is as a material. So that means yttrium and barium and copper. So then ultimately it is going to be dispersed in the water. It will form the solution state. The solution state it is going to be metal ions. The metal ion it is going to be, so once we are going to be add the extract, the orange peel extract, then ultimately it is going to be reduce the metal ion. Then the reduce the metal ion it is going to be, it will form the reaction it is going to be carried the temperature, it will form the gel formation. Then ultimately it is going to be precipitate, it is going to be formed. The precipitate is going to be collected and then it is going to be heated into the oven. Then ultimately it is going to be calcinated. The polyphenol it is going to be, so it is going to be giving the high temperature. It is then high temperature it is going to be vanishing of the gases, it is going to be converted. So that means desired stable structure of the material is going to be formed. So that is the general process of the material preparing of the YBCO superconducting material, the plant extract. So once it is going to be from the desired structure, it is going to be huge application of the so because of the material it is going to homogeneity. So smaller size of the material, the smaller size of the material, ultimately it is going to be huge. High surface of the volume of the material. The high surface of the material it is going to be superior activity of the material. So we can apply for the energy storage. So energy storage application also it will be based on that it is going to be material. So it will be applying for the various application for the energy related work also it is going to be work. Yeah.
Okay, thank you for your presentation. It was very interesting and insightful.
Thank you.
Okay, thank you, Sarina, for your questions. Estamos con estudiantes de Kazajistán. Now, Simbat.
Hello, thanks for this presentation.
Can you
it was
activate
really
your
interesting
camera,
for
please?
me.
Yeah, can you
The
activate
question
your
is, how many different samples did you...
Simbat, can you activate your camera, please?
Okay. Hello.
Hello, hi.
My question is, how many samples, these synthesis samples, did you prepare in total?
So total it is around YBCO superconducting material, 5 material we prepared, solid method, grain method and solid state method, and incorporation of the tinoxide material in the YBCO material, and lower amount, higher amount, that is 5 sample, And so iron oxide nanomaterial, the functionized group material, it is going to be prepared. So 3 material, so 8 material, so 8. And so titanium dioxide material is going to be prepared. So 3 material, around it is 11 to 12 so compounds we prepared.
Thank you.
Yeah.
Thank you very much, Simbad. Now, Jaroslav, a question?
Okay. So can you see me?
Okay. Not yet, but okay, but you can continue.
Okay. So thank you for your interesting presentation. I have a question about this one. So
I think that he has some problems with his, I think he's called Robert, but is here. Divinov Yaroslav, it is. Okay, but I will try to read. He sent me his questions. He said, are you there? Okay, go ahead.
So my question is partially related to the topic. There is yttrium, barium, copper oxide, but there is also lanthanum, barium, copper oxide. So what do you think? Which of these oxides is better suited for nanotechnology and green chemistry? So in other words, like which one is more environmentally friendly to use?
Yeah. Okay. So we are used for the more environment friendly. It is going to be green method. So while looking for the green method, so we only use it for the plant extract. The plant extract, it is going to be is eco-friendly to the environment, and required temperature it is going to be very less, and the rapid reaction it is going to be occurs. So the metal ions, that is barium, yttrium, and copper, it is going to be reduced. For the reduce, require the reducing agent, right? So the metal is there, the metal it is going to be oxidation state, so different oxidation state. So that means the metal ions it is going to be reduced by the reducing agent. For that it is going to be require the reducing agent. So generally it is going to be in the looking for the chemical method, so where different organic reducing agents, sodium borohydride. So that is the organic reducing agent. So it will be reduced. So some other reducing agent also, the chemical it is going to be, so that is the reducing agent. So reducing agent is going to be eco-friendly to the environment. So here it is going to be the reducing agent. The metal ion it is going to be oxidation state. It will be reduced by reducing agent. Reducing agent is going to be used for the plant extract. The plant extract it is having the polyphenols. The polyphenols it is going to be acting as the reducing agent. Then ultimately the polyphenols it is going to be reduce the metal ion. That is the eco-friendly to the environment. By looking for the chemical method, there are the different types of reducing agent. Then ultimately it is going to be we are applying for the to the metal ion the solution state. When it is solid state method, so soluble method, the solution state applying for the reducing agent, it is okay. So it will be releasing of the gases. Why? Because the reducing agent, the proper required solvent it is needed. We are applying for the distilled water. So some distilled water is reducing it, some organic reducing agent it not dissolving to the water. If it is going to be another solvent, which it is exactly it is going to be which solvent it is suitable for the which reagent is going to be. So then only it is going to be applying for the metal solution. Otherwise it is going to be, if you going to other solvent we are going to be dispersed, what happened? It will be releasing of the toxic gases to the environment. So reducing agent, the proper solvent it is going to be required. Otherwise it is going to be that also it is going to be once reaction it is going to be occur, applying for the temperature, it may going to be the temperature. So for that chemical reaction of physical method, they are going to be applying for the fume. They are applying for the chamber. So that is the okay. Why? Because the required temperature and pressure it is going to be applied. So huge. So releasing of the gases to the environment. So that is the more issue. So that is the so his pollution, it is going to be reaction occurs into the environment while applying for the reducing agent. So while looking for the plant extract, it is where reaction it is going to be carried out the room temperature. So that means more eco-friendly to the environment. There is no pollution to the environment. So that is the more and more advantage to the preparation of the material. So even it is YBCO material or nano material. So that is the more advantage while looking for the green method. So that is the advantage. So while compared to the physical and chemical method, even it is superconducting material. So that means it is going to be preparing of the material. So carried out at the room temperature, it is going to be. So we'll get the desired product of the material. So eco-friendly to the environment. So that is the more advantage. Yeah.
Okay, thank you.
Yeah.
Okay, thank you, Livnop, for Yaroslav, por your question. Gracias a los estudiantes, la participación de los estudiantes kazajos. Es con nota. Okay, thank you for your participation, the student from Kazakhstan. You have your grades now, or your scores. Okay, now, Ximena, is there any question from the public, from the online?
Good morning, Professor. Well, good day. We don't have any question from our social network. Thank you.
Yeah, thank you.
Okay, well, thank you very much. Narsi, do you have last words to say goodbye, maybe, to the public?
So, yeah, thank you. So, thank you very much for kind attention to listening my presentation. Thank you very much for one and all. And also, finally, I really thanks to the Concitec to giving great opportunity to me today. I'm here, University of Hyderabad, Peru, Lima. I really it is thankful to the Concitec providing opportunity, and also really thanks to the Professor Luis Santos. Today I am here. So that is very grateful thanks to the Professor Luis Santos, and also a grateful thanks to the Professor Angelo Bostomana. So providing this opportunity to me. So one and only. So still it is going to be continuously going to work. So really it is going to be thanks to the Professor Angelo Bostomana, Professor Luis Santos, and I really thanks to the Concitec Presidia giving this great opportunity to me. Thank you very much. Thank you one and all for all.
Narsi, can you stop sharing your screen, please? Because we are going to open our cameras and our microphones to say goodbye. But first, you can stop sharing your screen, please.
Yeah.
It is on the bottom, on the center. It is stop sharing on the red icon.
Yeah.
Okay,
yeah,
nice. Okay, everybody, please open your camera and your microphone to say goodbye to Dr. Narasaiah Boya. Want to see if you are present. Your microphone and say goodbye to Dr. Narasaiah Boya.
Bye.
Yeah.
Goodbye.
Thank you.
Thank you.
Thank you all.
Bye.